Hi again, and welcome to Lesson 5 on Designing Database Solutions with Microsoft SQL Server 2019. For today's topic, you are going to learn the concept of database normalization to start organizing your data into several connected tables properly. In doing so, you'll understand the use of foreign key constraint and learn how to create it using the database diagram tool of SQL Server Management Studio. At the end of this lesson, you should be able to create a database that consists of at least 5 related tables, showing one-to-one, one-to-many, and many-to-many relationships. Database normalization is the process of structuring a relational database in accordance with a series of so-called normal forms. This is done in order to reduce data redundancy, thus improving data integrity. This concept was first introduced by an English computer scientist, Dr. Codd, as part of his concept of relational model for database management in 1969. Normalization is accomplished by applying some formal rules in organizing the columns and tables in a database, either by creating a new database design, known as synthesis, or improving an existing database design, known as decomposition. Its main purpose is to eliminate data redundancy and undesirable characteristics like insertion, update, and deletion anomalies. While there are several normal forms that existed since 1970s, I will only highlight 3, the first, second, and third normal forms. If you try to read some good books on this topic, you will see that data normalization is actually a mathematical process with some complex principles behind in order to get your database in a so-called normalized state. Well, I'm not going to explain these concepts theoretically, but I'll illustrate it in a more practical approach and summarize it a bit. You just have to focus that the main idea behind why we need to normalize our database is to simply achieve the following: to minimize duplicate and redundant data, and to ensure proper data dependencies. To achieve the first normal form, you must satisfy the following. A table should have a primary key that distinguishes each row as unique. Each field should contain only one value. No repeating groups or repeating set of columns containing similar values in a table. Suppose we have a table called companies where we store information of our partner companies. So far, the design is good. We have a primary key that identifies each record in this table. Each field only pertains to a single value and there's no repeating group of information. Say we decided to add another important field, contact person, so that there will be a specific person to contact for each company. And again, there's nothing wrong with this. So far, so good. But then what happens if we want to add another contact person in one of these records? Say, for Microsoft Corporation, I want to add 2 more. Then you might be tempted to do this. And now, this violates the first normal form, where each field should contain only one value. Although your database table will not trigger any error or something when you save this, but if you plan to store your records this way, you'll have problems eventually. This design leads to data inconsistency and record anomalies. So if you think of another way, you might be tempted to do something like this. Well, again, this is a bad idea as well. It violates the first normal form that says no repeating groups. Here, we have repeating set of columns containing similar values in a table. It is bad because the table structure is not maximized. It might be okay for a company with 3 contact persons, but a waste of space for others with only 1. So, to address this issue, we must create another table for contact persons and then simply provide a reference to the company's table like this. And now, you get a taste of why it is called relational database model. In a relational database, there are 3 relationships that exist. The common that you'll encounter is this, one-to-many relationship, wherein, in this example, one company can have 1 or more contact persons. This is similar to the concept, one product can be ordered several times, or one customer can have many orders. In other sense, you can also use the term many-to-one, as in, 1 or more contact persons can be assigned to only one company. In this illustration, both tables adhere to the first normal form. Each has its own primary key that is unique for each row. And the additional field here in the contact persons table used to reference rows from the customer's table is called a foreign key. A foreign key is a key that is used to link 2 tables together. It is a field or group of fields in one table that refers to the primary key in another table. When you structure your tables like this, you must explicitly define a foreign key constraint to provide referential integrity, such that a contact person cannot be added on the list without a company to reference. Or, we cannot just remove a company record without first removing all records referencing it from the other table. Eventually, you will come across table designs that involve primary key consisting of multiple fields. This is also known as composite key. Consider the following table. Suppose we want to store information of seminars that we will be hosting. We have the seminar ID, the date, the title of the seminar, remaining slots, and the room where it will be conducted. Now, suppose we allow the same seminar to be repeated, but it has to be conducted on a different date. With this rule, we cannot use the seminar ID as a primary key because it does not uniquely identify each record in this table, meaning it is repeated. But the combination of seminar ID and date field make a unique value that we can use as a primary key. This is known as composite key. So, what's wrong with this table? Although it looks good, but the second normal form states that any non-key field should be dependent on the entire primary key. And in this illustration, we have the course title, remaining slots, and room fields as our non-key fields. And if you investigate further, course title is only dependent on the seminar ID field and not on the entire primary key. This leads to data inconsistency. Suppose that the seminar ID is changed to DSA 101 instead of SQL 101. So the biggest question is, which one is correct? Is it the ID or is it the course title? We now created an inconsistent record, having the same course title with two different IDs, or the other way around, two different IDs pointing to the same course title. So to achieve the second normal form, we have to break this into two tables, say seminars and courses, and simply provide a reference to this course ID in the seminars table. When you do something like this in the seminars table, this composite key is also known as compound primary key because the seminar ID field serves as a foreign key that is linked to the primary key in another table. So, changing SQL 101 to DSA 101 won't create inconsistent record because SQL 101 only points to a course title of Intro to SQL and DSA 101 only points to data structures and algorithms. The third normal form states that no non-key fields are dependent on another non-key field. Consider this example. This is the same table illustrated earlier. I've modified it so that it only has one field that defines as primary key. And then the course ID is a foreign key that references the primary key in the courses table. Same as with the previous illustration, combination of course ID and date make it unique. And the remaining three fields are considered to be non-key fields. Now, one of these fields violates the rule in third normal form. If you take a look at the capacity field, this field is entirely dependent on another non-key field, which is the room field. This leads to a potential data inconsistency again. If I change this capacity to a different value, then which one is correct? To avoid this kind of potential problems, create another table, say rooms, that only holds information pertaining to rooms. Then, simply reference it to the seminars table. Having a good understanding of these three normal forms lead to a good database design. This makes your database easy to maintain, promotes record consistency, and won't create garbage data. For you to remember this concept easily, database normalization is summarized as this: the key, the whole key, and nothing but the key. So, help me code. Aside from the one-to-many relationship that you'll encounter most often, there is also the many-to-many relationship and the one-to-one relationship. To understand the many-to-many relationship, consider the following illustration. Suppose we have two tables that store the authors and the books, and say for example, author Joe Edgo wrote 2 books, database design and data structures. Then, Mark Sam wrote 1 book, Microsoft Excel. To relate the two tables, we could add another field called author that serves as a foreign key to this books table. This creates a one-to-many relationship. But what happens if there are books that were written by multiple authors? Say, if Data Structures book is now written by two authors, Joe Edgo and John Doe, then you might be tempted to do something like this. This violates the first normal form that says no repeating groups. And you cannot do this either. To resolve this, we must create another table that serves as a junction table for the first two tables. And by convention, its name should be the combination of the two table names, as in authors books or books authors. These first two entries mean that author 101, which is Joe Edgo, wrote two books with IDs 1 and 3. However, records 2 and 3 simply says book number 3, Data Structures, has two authors, Joe Edgo and John Doe. The author ID and the book ID in this junction table make a compound primary key, similar to a composite key, but these fields are actually foreign key fields that make up as primary key. Some database designers use additional single field to refer as the primary key instead of using a compound primary key like this. Another relationship that exists is the one-to-one relationship. This is less common as compared with the one-to-many relationship because you can literally merge all information in just a single table. But there are situations that you might find this relationship beneficial. In a one-to-one relationship, one record in a table is associated with one and only one record in another table. So, why separate the information into two or more tables if the fields only pertain to the same record? Consider this given illustration. Suppose we have an employees table where we store all the information of employees for a certain company. So you have employee ID, last name, first name, and so on. But what happens if you have different types of employees that require different sets of attributes to be stored? Say, if this company is an academic institution, then we could have teachers as an employee, wherein teachers have specific information that are not applicable to other types of employees, like regular office staff. Then you might suggest, why not create two separate tables for teachers and office staff? Well, that's actually good. But now notice that there are similar fields that existed in both tables. So, to resolve this, you can apply the concept of inheritance by using a one-to-one table relationship. You can extract the common information for both tables and place it in a separate, more general table, say employees, then retain only the specific attributes for each type. Since both teachers and office staff are employees, they must refer to the same employee ID and have a one-to-one relationship, which means this teacher is the same as this employee since it only refers to a single existence of the same ID. In other situations, you don't need to apply the concept of inheritance to achieve a one-to-one relationship. You can simply break a single huge table into two or more smaller tables for performance gain, as bigger table structures sometimes require longer time to cache and could reduce access time. So, let's use our SQL Server Management Studio and start applying these concepts. I've already created a database for this, Lab Activity 04, and inside it, it initially consists of only one table, Employees. Let's take a look at the design. It has 4 fields, Employee ID as the primary key, last name, first name, and contact number. Also, I've already entered 5 sample records for us to work with, from Employee ID 101 up to Employee ID 105. To start designing your database visually, right-click on Database Diagrams folder and select New Database Diagram. When a dialog box appears, simply click Yes, and this opens a dialog window that lets you select from existing tables in your database to be added in this diagram. Since we only have one table, I'll select it and click Add, then close this dialog window. In this database diagram, I have added the employees table. You can click and drag your tables here as you like and position it anywhere. If you want to see the standard view of this table and not just the column names, you can right-click on the title bar, Table View, and select Standard. This is the same view that you see when you edit your table in the Table Design view. Since we're going to add several tables here, I'll resize the column width of this table so it doesn't occupy too much space. To add another table in this diagram, right-click anywhere in this empty space and click Add Table. If you have existing tables that haven't been added yet, you can select it from here. However, the only table that we have has been added already. So I'll just close this one. And to create a new table, we can do it directly from here as well. Right-click anywhere and choose New Table. So I'll create a new table named Teachers, similar to the one I illustrated earlier. This table will have one-to-one relationship with the employees table through this employee ID field. I'll use the same data type int, right-click and select Set Primary Key. I'll add the remaining fields that are unique only to teacher employees, such as academic rank, rate per unit, and department. To illustrate the one-to-many relationship, I'll set the data type of this department to char3, which means it can only store 3-character code of the department. And then, what I'm going to do is to create a reference table for this field called departments. I'll resize the width of this teachers table as well and rearrange it a bit so we can fit everything in the screen. Now in the departments table, I'll create the primary key field, depth code. This will be the same 3-character code that I'm going to reference in my teachers table. The name field for the actual name of the department. For example, depth code is ISP and the actual name is Information Systems Program. I'll have another field here, contact number. This is the contact number for department that is different from the contact number of employee. I'll make it nullable and I'll resize this one as well. To create a foreign key constraint between these two tables, simply click on the primary key field from this reference table and drag it down to the field that will serve as the foreign key. And once you release this mouse button, a dialog window appears asking for the tables and the columns that will be linked. It gives us a suggested foreign key name of FK Teachers _ departments. You can verify if these are the tables and columns that you really want to link. The primary key table is the departments table and depth code is the primary key. And then the foreign key table is the teachers table and the department is the foreign key field. Well, this is what we wanted. Simply click OK. And in the foreign key relationships dialog window, you can still access and modify the tables and column specifications that you just saw earlier. We can see that the enforce foreign key constraints is set to yes. And in the insert and update specification, you have the delete rule and the update rule set to no action, while you can change it to cascade, set null, or set default. But for now, leave the default so that you can see how foreign key constraint restricts you from referencing records that don't exist. Just click OK and in your diagram, you'll see a relationship link between your departments table and teachers table. The information is shown when you hover your mouse on it. The key symbolizes one entity and the infinity symbolizes many. So, this link indicates a one-to-many relationship between these two tables. You can click and drag this link to position it anywhere as you desire. This is just for visualization purposes. It doesn't affect the actual foreign key relationship settings that we have defined already. Now, let's create another foreign key constraint between this teachers table and this employees table. I'll click and drag the employee ID from the employees table to the teachers table. Same dialog window appears, and it looks good to me. Employee ID to employee ID. I'll leave the default setting as well and click OK. Now let me rearrange this link for you to visualize properly. Although it is not necessary to do this, but it is a good practice to place the link in the fields that it represents to understand your diagram easily. So, both ends of the link show a key which indicates a one-to-one relationship. And to show a many-to-many relationship, I'll create another table, Meetings. This table will hold the information pertaining to all the meetings that a certain employee can attend to. First, I'll rearrange this one to have more space. So this table must have a meeting ID of type int and set it as primary key. A meeting has a date, time start, time end, meeting venue, and a meeting agenda. I'll resize this as well, and so far it looks good. Now, consider the scenario. Suppose one teacher can attend to one or more meetings, and on the other hand, one meeting can have one or more teachers that will be attending. So, to satisfy this scenario wherein both tables have one-to-many relationship with each other, a junction table must be created. I'll call this table Teachers Meetings, or much better, Faculty Meetings. It should reference the employee ID from the teachers table, so in here, I'll use faculty. It doesn't need to be the exact field name. What matters is the data type. When linking two fields, the data type must be the same. And then, meeting of type integer as well. Now, I'll select both fields, right-click, and set primary key. And we've just created a composite key. I'll resize it as well. By the way, you can use this cross-haired pointer located at the bottom right portion of your window to have a quick view of your entire database diagram. This is very useful when you have a database diagram that consists of multiple tables later on that don't fit on a single screen. So to create a many-to-many relationship, click and drag the primary key from the reference table down to this foreign key field. And click OK. I'll do the same thing for the faculty field to the employee ID field. It doesn't matter which of these two tables, the employee ID field is the same. You can verify the fields if correct, and then click OK. I'll rearrange the link for better visualization. Now the two composite key, faculty and meeting fields, are said to be compound primary key, because we have used it as a foreign key that references the individual primary keys from the two tables, and that's the difference. One more thing, I'll make this meeting ID to be auto-incremented. To do this, I'll click this toolbar to display the properties window and set the identity specification to yes. One important thing to remember, this diagram is not yet saved. You can see the asterisk appearing in each table. So I'll save it first and give it a name Employees Meeting Diagram. And when I click OK, it gives me a warning that the following tables will be saved to my database. And yes, this is what I want. So I'll click yes, and then I'll refresh the tables folder, and you'll see all 5 tables were successfully saved. When adding records to tables that are related to one another with a foreign key constraint, you must prioritize first the reference or lookup tables. For example, if I want to add an entry to this faculty meetings table, then I need to enter record to this meetings table first, as well as to this teachers tables first. And it makes sense. How can we have a faculty meetings entry if we don't have at least one faculty or we don't have at least one set meeting? But take note, if we create an entry to this teachers table, we have to make sure that we already have an employee first, because teacher's employee ID will be coming from the employees table. Similarly, I need to have department's records first, so that teachers can be assigned to it, as in one department can have one or more teachers. Let's check the departments table, as well as this teachers table. Both tables are empty. Let's take a look again at our employees table. So we have 5 employees so far, employee ID 101 up to 105. Now, suppose employee ID 102 is a teacher with an academic rank of Associate Prof 4, a rate per unit of 950, and if we try to place a department here, say ISP, wherein this department doesn't exist yet, then it will throw an error saying conflicted with foreign key constraint. And this is the example of referential integrity. Having a foreign key constraint, we must create first a department with depth code of ISP. The department name is Information Systems Program. And let's have a dummy contact number. I'll add another department, CPE, Computer Engineering Department, and a contact number. Now, if we go back to the teachers table, this first record should work fine because now this record was able to reference the department value of ISP that matches one of the primary key values in the department's tables. Let's create another teacher. I'll use ID 103, instructor 2, 435, and the department is CPE. And then last one, and the department is ISP as well. So far, we have records for the department's table, employees, and teachers tables. Now, I'll add new meeting records, say Feb 25, 2021, from 9:30 to 12 at room 7 with agenda of curriculum development. Next meeting is on Feb 26, 8 to 9:30 at conference A, agenda of syllabus content. So far, we have 2 meeting IDs and we have 3 teachers. To populate the faculty meetings table, we use the meeting IDs and the employee IDs that existed in both primary key tables. Say, teacher with employee ID 103 will attend the meeting ID number 1, so as teacher 104. However, teacher 102 will attend the meeting ID number 2 as well as teacher 104. And this is how you're going to populate your junction table in a many-to-many relationship. By default, our foreign key constraint setting is set to no action. And when we try to update or delete records from the reference table, this will be the effect. If I try to delete this record wherein it is being referenced by at least one dependent table, it will not be allowed because it violates the foreign key constraint. This is the benefit of referential integrity. In this example, you are not allowed to delete this record because records in the faculty meetings table will be abandoned. This will result in what we call orphaned records. And sure, we don't want that our teachers will attend to a meeting that doesn't exist. Similarly, if I want to modify one of the primary keys in the departments table, but since it is already being referenced, then SQL Server will not allow it. You cannot change this one either to a department code that doesn't exist. And if you really want to change it, you must first delete the foreign key constraint and then change this to anything you like, and this will now be accepted. But you have to understand, without this foreign key constraint, any value can be placed here, thus you lose data integrity. So, when working with relational database model, make sure that correct relationship is applied and foreign key constraints are enforced. Up next, let's start writing queries that retrieve records from multiple tables. Again, thanks for watching. If you learned something of value here, please click the like and subscribe button for more programming tutorials. This is Joe Edgo, and hope to see you in the next video lecture.